Today we are very glad to have Dr. Bethany McDonagh from SEMCC. The SEMCC is a Euro-Mediterranean Center for Climate Change, Bologna in Italy. Bethany is now a postdoc at SEMCC in the Regional Ocean Focusing Division. She completed his master in atmosphere, ocean climate at University of Reading, and then did her PhD at the University of Bologna and the CMCC. Her PhD work is mainly about tides in the Mediterranean Sea. During her PhD, she also visited the Ginsong's group as part of her work on tides. And today, her topic is about internal tides in the Mediterranean Sea. Okay, yes, welcome.
Okay. Thanks for the introduction. Yeah, so today I'm going to be talking mostly about the latter part of my PhD work, which we formally finished about a year or so ago, but we've been doing a bit of additional analysis and we've submitted a paper in that time. So yeah, this work was mostly done at CMCC, but also during a visit I did in 2023 to the Max Planck Institute, where I collaborated also with Song. And yeah, I'd also like to thank and acknowledge the help of my PhD supervisors, Emanuela Clementi from CMCC and Professor Nadia Panadi from the University of Bologna. So today, my talk is mostly about internal tides in the Mediterranean Sea. I'm also going to add some additional kind of background and context from the earlier part of my PhD, which was what led us and motivated us to do this work to begin with. Okay, so to start at the beginning, why are tides important? What are internal tides and why are they important? So tides are quite a recent addition to many global ocean models. But they contribute a really huge amount to the energy budget of the ocean, along with wind. So we know that tides are essential for mixing and overturning the ocean, and also that they produce further internal waves. These are internal tides, or also called baroclinic tides, and they're usually formed at shelf breaks, ridges, and narrow straits, and they're estimated to dissipate about 1 terawatt of energy around the global ocean. Internal tides can dissipate in various ways. They can dissipate close to the generation site, usually if they're high mode internal tides or if they're sub-inertial, or they can propagate for hundreds or even thousands of kilometers away from the generation site, in the case of low mode and super inertial internal tides. Internal tides are also thought to be important in deep ocean mixing. So basically, we need to consider all of these processes in order to accurately model the ocean and especially to model the mixing. So to talk about internal tides a bit more specifically, as a general introduction, as I said, the barotropic tides, which are those that are independent of depth, the ones that are driven by the sun and the moon, then inform internal tides when they reach rough topography, shelf breaks, straits. And then internal tides can be kind of generalized into low mode and high mode. Low mode internal tides have longer wavelengths. They can propagate far away from the generation site, and they contribute to remote mixing, which is often not parameterized well in ocean models. And they represent around 70% of internal tide energy. There are also high mode internal tides, which are probably better parameterized in most models because they contribute to the local mixing, and they're about 30% of the energy. So basically understanding where these internal tides are generated, propagated, dissipated around the ocean is important for understanding and closing the energy budget. Mapping internal tides can help us make decisions also about modeling this dissipation. So if internal tides are propagating on large scales, we should consider that when we're thinking about mixing. I'll also show this short, small movie. So internal tides can be visible also on the sea surface, especially in regions where they have a really large amplitude. So you can see them with satellite altimetry, but really they're mostly something that's happening in the deeper and intermediate layers of the ocean. So now to move on to think about the Mediterranean Sea specifically. So what do we know about tides in the Mediterranean Sea? So firstly, Mediterranean sea tides are mostly quite low amplitude. However, they have quite a range of known impacts already. So we know that tides increase the salinity and decrease the temperature of the water flowing into the Mediterranean Sea from the Atlantic Ocean through the Gibraltar Strait. And this is the only entrance and exit to the Mediterranean Sea from the open ocean. So anything that's modulating this inflow in terms of the flux, but also in terms of the traces, is really important for the Mediterranean Sea overturning circulation. We know that internal tides are generated at the Gibraltar Strait and the Sicily Strait. We also know that some basin modes or seiches, which are standing waves in semi-enclosed and enclosed basins, have similar frequencies to tides. So this could also be important when we're thinking about tides. We know that tides also change the deep water outflow of the Mediterranean Sea. So in the Mediterranean, we have inflow at the surface from the Atlantic and then outflow of saltier water in the deeper layer. We also know from some literature that tides do have other nonlinear effects in the Mediterranean. And this is kind of where we started at the beginning of my PhD, is how are tides affecting the wider Mediterranean Sea dynamics? So we know what amplitudes the tides have, but what else is going on? And are the effects of tides limited to the spatial and temporal scales of the barotropic tides themselves, or are they impactful across other spatial scales? And then we started thinking about internal tides later. So are internal tides widespread in the Mediterranean? There were no studies except for local studies in the Gibraltar Strait and Sicily Strait mostly. So where else could the internal tides be generated in the Mediterranean Sea? And are they propagating over long distances in this region? And we decided to use two numerical models to investigate this. So first of all, I'm going to describe a bit the first half of my PhD, which was this paper, which was published last year in Ocean Science, to answer the first two questions that I mentioned in the last slide. So to do that, we ran two versions of our regional Mediterranean Sea forecasting model, but in the analysis mode, so not as a forecast. And this model is NEMO 3.6 with 1/24th degree, which is about 3.8 kilometres in this region. We have a high vertical resolution of 141 Z-star levels. The atmospheric forcing is from ECMWF, high resolution. We have 39 rivers and then open boundary conditions in the Atlantic and Diurnal Strait, which is the entrance towards the Black Sea. This model, the version with tides, has 8 tidal components which are forced in the model. So to analyze this, we ran 7 years, we used 5 years to remove a spin-up period. The experiment with tides was a slightly earlier version of our operational model, and we're comparing it to the same thing but without tides. We also analysed kinetic energy a bit, and we chose to focus on a few points in the Mediterranean. All of these points were available in the paper, but in this presentation, we'll just look at 2 contrasting points, which is the Gibraltar Strait here and the Cretan Sea in the east. So to start with the very top level, one of the first things that we looked at was the sea surface height energy density spectrum. So this is of the hourly sea surface height for the whole Mediterranean Sea. At a first glance, you see what you expect, which is with the tides that are in red in these plots, they're well resolved. You can see all of the 8 tidal components individually. That's great, but there's a lot more going on in this plot than just these 8 tidal components being added in the tidal model. First of all, we see the peak is broadened around the 12-hour frequency, which is this part here. And we think this could be maybe due to tides interacting with eddies and things like this. But then we also see other changes that are well away from the tidal frequencies, especially around 8 hours and 6 hours. And this was where things got a bit more interesting. So we then started looking at all of the seiche frequencies of the Mediterranean Sea. So these are all of the standing waves in the Mediterranean and its subregions and their various modes, which have been investigated in some older literature. And what we started to notice was that quite a few of these changes due to tides were happening at the same frequencies as the seiches in the Mediterranean Sea. So we started to think that actually some of these seiches are interacting with tides and some of them are being enhanced by tides. We also looked at this in a map form as well as in the spectrum. So here I've picked out two of the frequencies, which are seiche frequencies, where things were changed a lot by tides. So on the left, I show 8.2 hours with and without tides. And what we see is that we already know from the literature the two boxed regions should have seiches, but in reality, we see that that with tides, the SSH energy density changes a lot over actually the whole Mediterranean at this frequency. Again, at 6 hours, and especially in the Western Mediterranean, we see huge changes when we add tides, even though these are not tidal frequencies. So moving on from the sort of potential energy at the sea surface, now to look at the kinetic energy through the depths, we pick out some points of interest to do this part of the analysis. So I show here two spectra, but with all of the depths shown, so the contours show the energy density, firstly of the Gibraltar Strait at the top and the Cretan Sea at the bottom, with no tides on the left and tides on the right. So in the Gibraltar Strait, we kind of see what we expected from the literature. So tides are completely changing the spectrum here and increasing energy at many frequencies and at many depths. So we're seeing some internal tide activity as well here. In the Cretan Sea, we see something kind of interesting, which is that the near inertial peak seems to be impacted by tides. So the green line that I show on the slide here is, oh yeah, I see the mouse. Yeah, the green line that I show here is the inertial frequency. And what we're starting to suspect here is that there's some interaction between tides, or maybe internal tides, and near inertial waves, because we see that the inertial peak, which is clear in the no tides model, seems to be redshifted slightly in the version with tides. So we also plotted some Hofmüller plots to investigate this part a bit further, and we just go down to 1 month here to really look into detail. So in the Gibraltar Strait, we see exactly what we expect, but in the Cretan Sea, we see this interaction between near inertial waves and internal tides. So what we can see is that in the model without tides, we can see this wave propagating downwards slightly here, which is at a near inertial frequency. And when we add tides into the equation, at these intermediate layers especially, we start to see a wave-wave interaction between the near inertial wave and the tide. So to summarize this first part, which I've just gone through some of the key results, we find that tides can interact with basin modes in the Mediterranean Sea, and this really needs to be investigated further with a state-of-the-art model recalculating the basin modes. And this is something that others in the group are working on now, so we can look out for that later. We also found that internal tides seem to be maybe a bit more widespread in the Mediterranean Sea than the previous studies have found. And we see that internal tides can interact with near inertial waves in the Mediterranean Sea, which is another area for future work, I think. So now, after all of this, we decided that internal tides deserve a deeper look. So we started then looking at these later questions. So where are internal tides generated and propagated in the Mediterranean Sea? So this was part 2, the last chapter of my PhD thesis, which is currently in review at Progress in Oceanography. So hopefully it's going to be published soon because we finished the revisions. And for this, because I was visiting Jin Song's group at the Max Planck Institute, we decided to use 2 numerical models to analyze internal tides. Firstly, the tides version of NEMO that I already described, and secondly, a 5-kilometer run of ICON as well. And this was great because it meant that if these 2 models had some agreement, then maybe we could increase our confidence in what we found. And also, if these models differed, we could try to understand why. And we could understand what about these models is making the internal tides represented differently in the across the 2 models. So the version of ICON I used was 5 kilometers, which is the R2B9 resolution, which had 128 levels. It's a global model, so we don't have any boundary conditions, but for this analysis, I cut out the global model just to the same region that NEMO already has for a direct comparison. The tides are quite different in ICON than they are in NEMO, which could be an important reason for differences between the two models. The atmospheric forcing is also different. They use ERA 5 and ICON, and we use the same time period for the analysis. So one of the first things to look at was the generation of internal tides. And to understand the generation of the internal tides, we used this conversion rate C, which I put in the green box here. Without wanting to go through all of the theory in a lot of detail, the conversion is basically, it can be used as an estimate for internal tide generation. So for the amount of energy that's used for the generation from barotropic to baroclinic tides. And this is a combination of the density at the tidal frequencies and also the W at the tidal frequencies, which is extracted from the horizontal velocities. There's a couple of caveats to this. C probably should be positive according to theory. We do see some negative values, which could be due to things like interference between internal tides generated in one site and another, that could then make them go out of phase. This C value has been shown to be a good estimate for this conversion rate in the global ocean, but it hasn't been used in the Mediterranean Sea before, so it's kind of yet to be decided whether this is, or how useful of a measure this could be. And basically, we did a harmonic analysis of the currents and the density to calculate this, and then summed all of the 8 tidal components that are used in the NEMO model. So this was the kind of key result from this analysis, which is that the amount of energy available for the generation of internal tides in the Mediterranean Sea is around a couple of gigawatts, depending on which model you ask. So in NEMO, about 3.3, in ICON, about 1.5. The global ocean value for C is estimated at about 1.7 terawatts for reference. And from this, we basically see 3 key regions for internal tide generation in the Mediterranean Sea. Firstly, the Gibraltar Strait. We expected this, we already knew this, and here it is. Secondly, we see the Sicily Strait and Malta Bank, which is the region in the box around Sicily. And we see a lot of generation here along the ridges and along the Malta Bank, which has a very shallow bathymetry and then a drop to a very deep one of the deepest in the Mediterranean. And in the coloured contour plots, I actually show the bathymetry as well, so you can see how steep this break is. And then a third region for internal tide generation, which we think is totally new, is the one around the Hellenic Arc, which is around the western side of Greece and the bottom of Crete, which again is a break between the shallow Aegean Sea and the deep Ionian Sea. We also split this into diurnal and semidiurnal components, and this is because semidiurnal internal tides are able to propagate freely in the Mediterranean Sea, but because of its latitude, diurnal ones can only be trapped along the bathymetry or dissipate close to the generation site. So it's important to consider these two kind of separately as well as together. And this is where we really start to see the differences between the two numerical models, because NEMO has a huge amount of generation from the diurnal components, whereas ICON doesn't. And this is particularly clear in the eastern Mediterranean Sea and the southeastern, where NEMO has really widespread internal tide generation, and ICON is much more limited to a few spots. So this is where that 1.5 gigawatt difference in the internal tide generation basically comes from. In the semidiurnal components, the two models are quite similar. Okay, so after the generation, we need to look at the propagation. So for this, we looked at the baroclinic kinetic energy at the different semidiurnal tidal components. And here I show basically where it peaks, which seems to be at around 150 meters, where we see a really large number of propagating waves and tidal beams in both of the models. And this is down at about 150 meters. Some regions seem to have more of this. So along the coast of North Africa, in Algeria, in the Tyrrhenian Sea, which is north of Sicily. And we see that actually, especially in ICON. And then thirdly, we see a lot of tidal beams also in the eastern Mediterranean, in the Ionian Sea as well, between sort of Sicily and Greece. And we think that these are kind of propagated respectively from each of the 3 main generation sites. So along the coast of North Africa in the western Mediterranean, these are probably coming from the Gibraltar Strait. The Tyrrhenian Sea are coming from the generation sites in the Sicily Strait. And in the Ionian Sea, these are coming from the generation sites in the Malta Bank and Hellenic Arc. And these structures, I just show 150 meters because this seems to be around the peak, but they continue down to around 1,000 meters. And at the bottom, I show 1,000 meters. And you can see this is kind of where the Mediterranean becomes a lot smaller because there's many sort of intermediate level depths in the Mediterranean and not so much deeper ocean. So the Mediterranean Sea is closed from east to west at this depth, which sort of limits the ability for internal tides to propagate over a long distance. Finally, we also wanted to calculate the wavelengths of internal tides. And for this, we chose 4 tracks, which are along the tidal beams I showed in the last slide. And these are on the top right corner. So they're the Algerian Sea, Tyrrhenian Sea, and then I chose 2 in the Ionian Sea, 1 north and 1 south. Then we plotted the wave number spectra for the M2 components along these tracks. So what we can see is that the first modes are usually around 50 to 100 kilometres, and this is pretty comparable with global values from the literature, or maybe slightly shorter wavelengths than the global values. In ICON, it seems to be a bit shorter again, more like 50 kilometres than 100. There are some longer wavelengths present. There's some peaks around 200 kilometres as well, which is a bit too long for internal tides. And we think these are probably internal seiches, which have frequencies kind of close to the tidal frequencies, the ones that we investigated earlier. On the left, I also show NEMO without tides as a comparison. And you can see, particularly in the Algerian Sea, there's a peak that's present with tides. And then this is changed with tide as well. So this is probably not the internal tide at the longer wavelength. We also compared this to theoretical values, which I show in the table. And the peaks that we see in the model are mostly comparable to the theoretical values. So you're probably asking at this point, why are the models different? This was kind of the final part of the analysis. So there's a few reasons that internal tides could be represented differently in the models. We know they're not the same model, but to focus a bit more on internal tides, I looked at the stratification because a more stratified ocean allows for more propagation of internal tides. And what we see is that ICON has a higher stratification basin-wide than NEMO. And this could maybe be the reason that we saw slightly more propagation, especially in the Eastern Mediterranean, despite a lower generation. It could allow the internal tides to propagate more readily. However, we see this second peak in ICON. And unfortunately, I think this is not a feature in the Mediterranean Sea. I think it kind of starts to bring out how the ICON model is maybe a bit less well-tuned than NEMO to the Mediterranean Sea, which makes sense because the NEMO model is something that the group that I'm in has been developing for a long time, specifically for this region. And kind of to back this up, I show also the temperature and salinity profiles compared to some global ocean observational data sets. Another reason for differences between the models is, of course, model bathymetry. So I also show this, and we can see that in some key regions, which are the plots on the bottom right, there's quite big differences between NEMO and ICON here, and that, of course, can change the generation of internal tides at these sites. Finally, of course, another difference is the different representation of the barotropic tides. So here I'm comparing the 2 models to TPXO, and we can see that the placement of the amphidromic points and the exact kind of difference from TPXO is quite different in the 2 models, and especially in K1, where NEMO is slightly overestimating in the Adriatic Sea and Eastern Mediterranean, whereas ICON is slightly underestimating in the same region. And the placement of the amphidromic points also differs, which can cause quite big changes in the barotropic tides. We also compared to tide gauges. Luckily, since the Mediterranean Sea is quite a coastal basin, we have many tide gauges, and especially in the western part. And in general, NEMO performs a bit better compared to tide gauges than ICON. And like I said, I think this is mostly because NEMO is a model, this version of NEMO has been very well tuned for the Mediterranean Sea, whereas ICON has not been specifically tuned for the Mediterranean since this was a global realm of the model. So to summarize, we found that internal tides are much more widespread than we already knew about, and here they're mapped for the first time. The generation of internal tides is in these three kind of key regions, and the propagation of internal tides comes from mostly these three key regions. We can see that internal tides can propagate for up to hundreds of kilometres within the Mediterranean, which hadn't been looked at before. We also found that both models do show broadly similar features in the internal tides, which is quite good because we didn't know anything coming into this, and two totally different models have quite a lot in common. However, things like stratification, bathymetry, different tidal forcing does contribute to some differences between these models as well. So finally, I wanted to also talk about next steps, ongoing work, what are the questions of this work, because I think although we've answered some important questions here, we've also raised a lot more, even more important questions. So firstly, the connection to the basin modes in the Mediterranean Sea. We know that these are important, and we now know that they interact with tides as well. We also think they have baroclinic components, which are yet to be investigated. Somebody else in the group is investigating this at the moment. What we want to know is, how do they interact with internal tides? Can we do an analysis like this to find out more? And how is their energy distributed in the ocean? This is ongoing work in the group, and hopefully we'll get to do more of it in the future. Secondly, the connection to eddies. The Mediterranean Sea is quite eddy rich, and especially actually in the southeastern Mediterranean, where internal tides seem to be propagating a lot. So how do these eddies potentially interact with internal tides, maybe dissipate them as well? Understanding a bit more about the dissipation is an important next step, since we already looked at the generation and propagation, and looking at the dissipation will allow us to start to close the budget here. Something else that's going on in the group right now is development of a grid refinement in the Gibraltar Strait, so having a kind of kilometre scale resolution here. And this could help us to understand the internal tide generation there even better than we do now. We could also expand this to the Messina Straits, which is the small gap between mainland Italy and Sicily, which is not really resolved in our models now. We know that internal tides are probably generated here, but there's not really a model that can resolve it yet. And then finally, I guess the big question is then, how do tides or internal tides then interact with the Mediterranean Sea's overturning circulation? And this is kind of maybe one of the biggest questions that we have left. And hopefully we can start to look at this stuff soon, because we're going to have a new reanalysis product next year. So it will be our first one with tides. So I'm hoping we can start to consider this in the future. And that's everything I have to say. If anybody has any questions, discussion points, I'd be happy to talk about them. And also I'm here until the end of tomorrow. So I'm also happy to meet with anybody who wants to meet to discuss these topics and more. Thank you.